Hello, Boston. Hello, Quincy. Thank you for having me. It's a beautiful day outside, and I appreciate you all kind of hanging out here. It says something about, your interest level. If you want to hang in, check this out. I promise you, though, this will be interesting. This will be something I think that you'll really want to hear. So, as mentioned, I'm from Radius, and we're working on some technology that I'm going to jump into, but a little bit about myself. Early on, I worked at Circle from pretty much the beginning. Did a bunch of things there. Most interestingly, the cold storage system, and then I started USDC. So I was a team of three of us that did that. So that's been now USDC is like grown, but like it grew without me. They've done a much better job. That I can't claim that I started USDC anyway. But I'm very interested in digital dollars. Like, how do you get a digital representation of a dollar, and how do you put that on the internet? So I went to the Federal Reserve next. I realized that you have dollars, and there's 350 million-ish citizens of the United States, but that's ridiculous, right? There's actually 8 billion users of the dollar, potential user. The total addressable market is 8 billion, not 350 million. So what would it really look like to build a digital dollar that can really scale to that kind of a level? And so I did some work there. There's this project called Hamilton that I worked on. We'll talk about that, and then a sort of the evolution of that called Parsec. We'll go into that. Currently, I'm at the MIT Digital Currency Initiative, the DCI. I am a senior researcher, senior research advisor, I should say. And then also, as I mentioned, Radius. Radius is a startup, started in the beginning of this year, and we are working on productionalizing some of this technology. So let's dive into the problem that we've basically I've been hinting at here, right? So there's a lot of dollar-denominated transactions in the world today, right? There's cash, credit cards, debit cards, ACH, other lots of things. Turns out, at the Federal Reserve, there's like thousand some odd PhD economists, and you can ask them a question like, "Hey, Black Friday, most transactions ever going on. How many cash transactions are there?" And they have this deep network of information that they can go into, and they can actually tell you what the answer to that is. We all kind of know how much credit cards do and how much ACH does, and this is what they said: 20,000 transactions a second of cash. Debit cards are 60, credit debit, and then 13 ACH. Basically, if you all boil it down, you round things out, 100,000 transactions per second at peak. All right? And that's just payments. Okay. So 100,000 transactions a second. Let's talk about that for a second. That's ridiculous. All right? Why is that? Well, it needs to be orders of magnitude more when you have a bot that has some money in an account and it needs to move it. You can see that happening a lot faster. What about micropayments, right? If you could pay a penny to read a web page without ads, you might do that, and you do that a lot more than buying coffee. You can imagine IoT devices with accounts, et cetera. You get the idea. Basically, tens to hundreds of millions of transactions per second are really what the world is going to need, right? And again, that's just payments. There are many other things you can do. We can get into that later. So at the Federal Reserve and MIT, we came up with a solution to this. We worked on this project called Project Hamilton. The result of it is an open source code base called OpenCBDC. If you go to DCI MIT edu/OpenCBDC, you can see that you can see this project. We wrote a couple of papers about it. It's been presented at conferences, and it is also connected with an open source code base called OpenCBDC. That's on GitHub. You could just go download it and run it. So This was a system that we basically modeled after, generally after how Bitcoin works. It's UTXO based. So I'm going to like skip a lot of technical things, but there are a few you need to know. UTXO is unspent transaction output. Forget what that means. Basically, there's a bunch of bills, and each bill has a name on it, and the name is the person who owns it. And you can take a collection of these bills and update the name to whoever else, and now they own it. That's the way UTXOs works. That's different than the way your bank account works. Your bank account balance is whatever, and it can go up or down, right? There are positives and negatives to that. We built this system, we scaled it out. Turns out it kind of ran into a wall around 120,000 transactions a second that we could not get beyond. And then we realized, hey, the way to do this is just to not materialize a global order of transactions. I'll keep coming back to that. Materializing a global order of transactions basically commits to, if I buy a hot dog in California and you buy one in Boston, does it matter who bought it first? Not really. It matters if we use the same money, so we need that guarantee, but it doesn't matter if you bought it or I bought it first if we basically bought it roughly in the same second. Kind of doesn't matter. So that realization, by the way, if you can come up with a reason for why that is not true, like why you actually do need to know globally, I would love to hear it. I've been like racking my mind trying to figure out why that is. Oh, hot dog eating contest? Well, you still need to buy. You probably buy in bulk, so that's one transaction. I don't know. But they're all sort of local. You just can't use the same bills, So we built a system that doesn't materialize a global order of transactions, and that turns out to be able to scale linearly. So what that means is, like, you want it to go faster, you throw more computers at it. And we basically did that. It has some negatives. Not really programmable, and it's fairly inflexible. We said, okay, great, we have this system that goes really fast. I think we did 1.7 million transactions a second with this one. And then we said, you know what, we kind of want to be able to do other things. Why don't we try this, and why don't we try that? And like every time we looked at something, we said, okay, we have to destroy the thing, cut it all the way down to its studs, and rebuild from scratch basically the whole system. Sounds like a waste. Why don't, instead of us doing that, let's build this new thing, which we call Parsec, which is a virtual machine runner. So you can run any virtual machine, right? So we picked the EVM. Why not, right? It also runs Lua, and you can do other things as well. You can, like, literally any VM. You could do x86 if you wanted. But we stuck with the Ethereum virtual machine. Turns out there's all this, all these contracts that are already written. Wouldn't it be great if we could like run those at scale? And so sure enough, we did that with Parsec, and you are actually able to take a smart contract from the Ethereum ecosystem, off the mainnet or whatever, and run it unmodified with Parsec. Literally the only thing you do is change the URL in MetaMask from public Ethereum mainnet to Parsec, and it would work. It doesn't commit to a global order, just like the other system that we built. That is a big deal because, and let's rewind back to, remember I said UTXOs, these are like little bills, and each bill has a name on it, and we're just updating the names, right? There is no limit to that. As long as you're swapping one bill from one person to another, you don't run into a problem. But what if you're trying to use accounts, right? So we have a balance. We're going to push it up or down. Let's say we're paying, payroll. At some point, like if we're going to run out of money, I got to stop. And that's a problem. You're not going to be able to know when to stop if you kind of parallelize everything. So we have a solution to this. This system, as it shows, we got up to 118,000 transactions a second, and then we kind of say, okay, it's fast enough. It's fast enough to like do the things that we want to do. So we'll try some other things. We'll get back to that. Okay, so how did we do that? Well, I'm going to skip a bunch of this because I kind of want to get to questions as soon as possible because those are always interesting. Basically, we have sets of shards. All the data is put into like shards. It's broken up to shards. When I say shards, don't think blockchains. These are not blockchains. These are key value servers. And then we launch these agents, and they run the VM. That's like they would run the EVM, for example. So your user wallet sends a transaction to one of those agents, and then the agent finds whatever shards are involved in this transaction and coordinates a two-phase commit to settle that transaction. It can do that critically in parallel with thousands of other agents if you want. As I say, I'm going to skip a bunch of these things. The only thing I want you to look at on this slide is the stuff all the way on the left. So there's a transaction. It starts. It gets a ticket number, and that's a way to resolve conflicts. I'm not going to go into that. And then the EVM is running, and it's just basically doing read and write operations. Every once in a while, if it likes, it can take a read lock that it has and upgrade it to a write lock. But basically, it just does that until it gets everything set the way it wants. And it prepares that, says, okay, these are all the new writes I want to do. And then if we haven't run into a lock contention, it commits, and then we discard, and we're done. So that's how that works. And I could go into it more deeply. Believe me, I can, but I won't right now. So as I mentioned, I'm working at this startup called Radius, and Radius, the idea here is to rewrite that for productionalization. Like, how do we really, do that? And the code base that we have, by the way, again, Parsec is also open source. It's on GitHub. You can just download it and run it. That code base is a research code base meant to run a research load. So if you want to try, an AMM, like Uniswap at 1 million transactions a second, you can go and do it. Find that you're going to have a problem doing that, but you could. So in rewriting for productionalization, some of that has to do with key migration, right? We have to add all these things that enable. What is key migration? Well, if you have 10 shards and then you get a lot of load and somebody starts to put a lot of data in your system, you need to add shards. So you need to be able to move shards around, and you need to be able to delete them and stuff like that. You need to be able to auto-scale the agents, add more of them when they're needed, and shut them down when they're not. Some of this is relatively well known, but the key migration stuff isn't. There's some interesting ideas about flexible key replication. You could do keys that are heavily hit on a server that only does heavily hit keys. Keys are extremely large on other servers that are optimized for that. There's a bunch of things you can do. Critically, we can also operate this system as an L2 on Ethereum. That brings some unique challenges. For example, one of the unique challenges is, well, how do you create a fraud proof if you don't have a materialized global order of transactions? So we have a way to do that. So there's some interesting things there. So I said this would be interesting. Okay, well, let's talk about it. Back, if you look at what's available right now, I could imagine Solana is relatively fast, where they have 60,000 transactions a second. Let's just say that they could do 1 million with Fireblocks or something like that, or Firedancer rather. Mega ETH could go a lot faster, probably, maybe reach 1 million at the tops, right? Monad is another one. These are all, basically scaled EVMs, same idea, but they're doing it in a very different way. That could probably get into that range too, but they can't go to 10 million or 100 million or 1 billion transactions a second. So there's really only one way to do that, and that is not to materialize a global order of transactions. I keep saying it, right? Well, what do? Well, you actually materialize a local order of key updates. And so that's how we handle that problem. So now, you would imagine if you're Uniswap, right, you want to run a AMM, you're going to have to lock a root key over and over and over, because you're going to make sure there's enough assets in the pool to handle whatever transaction is going on. You can't just drain the pool down to 0 and say, whoops. That wouldn't work. So you do need to order those. We have a way to do that, but there's also this implication that as smart contract development gets more and more, like concentrated on. It's going to focus on, well, how do you parallelize the load? And so I think a lot of that has to happen. Uncontended load, like, this is kind of, what we're basically doing. Any number of keys can be written in parallel, right? So I'll just tell you about a test I did this morning. So we fired up a test this morning where we ran an ERC20 contract that sent money from one account to another account, pretty much a random account. They don't contend. And when you do that, you can spin it up. We spin up, I think for that it was about 4,500 computers all around the United States. And we were able to, I think that test was like 1.2 million transactions a second. We've done tests that get a lot larger than that, up to the 20, 25,000 computers all running together. And we can reach much higher loads as well, because it just literally scales linearly by adding machines. The last thing I'll talk about is a contended load. I kind of hinted a little bit of this. Don't want to get too technical, but like heavily contended keys have to be sequenced. We have a way to do that. We can pre-execute the EVM, find out what it's going to touch, and then we can sequence just those. Critically, when you do that, the other transactions don't block. They can be parallelized while that's happening. And then as I said again, we don't commit to a global order. We certainly do not want to do that for non-contending transactions, because that would really create an issue. And then, as I mentioned before, you can have shards that are really fast, or shards that are really big, or shards that are kind of transient in nature, shards that are private even, which is a cool idea. Some of these slides got a little small, but you get the idea. So there's some interesting ideas, and I'll jump to questions because we don't have much time. Like I said, permission keys. What if a smart contract could actually hold a private key? So it could actually sign things. That would be really cool. Yeah, you can actually do that. We can run any VM, not just ones made for smart contracts. When you run VMs for smart contracts, they're made really interestingly. They're made to maintain just a collection of keys that just that smart contract can control. And that's what you want, because you don't want some random person to just update their balance to whatever. So that's a valuable design space, but you can violate it. You can actually go out of that. You can use things that don't normally happen, like you can harvest randomness. You can directly read the internet without an oracle. There's some fun things you can do. The last one that I'll mention here is a UTXO system, and essentially a balance-based system can use the same state. If you think about it, a UTXO is a create, read, delete. That's it. You can make the bill, you can read the bill, and you can delete it. And then it gets recreated somewhere else. That's it. There is no update. With a balance, that's a create, read, write, delete. So you could have two systems that use the money in different ways. One thinks of it as a UTXO, and the other thinks of it as a balance. This is actually possible with systems like this. Those are some interesting ideas. Thank you very much. I'm going to jump to questions because they're always fun and we're always running out of time. So let me do that. Thank you.
Hi, Anders. Great talk. You never disappoint. Thanks for coming. Earlier in the week, we heard a presentation from a prior presenter about the CBDC work at the Fed. So I want to kind of channel your thoughts on this one. They really thought that when the U.S. government launches their CBDC, it'll be the ultimate kind of spying, and like there will be no privacy. Almost what I think we hear what the China CBDC would be like. I'm sure you've heard this before. It's not my bingo card that CBDCs would become political, but here we are in 2024. They are. I'm curious, given your work at Project Hamilton and other places, what's your view on that type of perception that's out there? Both that's probably myth, maybe some fact. You're on the inside. What can you tell us? Thank you.
Yeah. So good question. I will of course, preface this by saying, certainly, no question about it, I do not speak for the Fed. I never have. Just so that's clear, these are my personal opinions. Yeah, so it turns out that the technology can supply unbelievable things. Unbelievable things. Like you would not think that they are possible. However, that probably is not common knowledge. And people rightly are concerned. And so I don't think it's a question of whether or not the technology can do it. In my opinion, it's probably possible to make something far more private than what we really even have today, even with private cryptocurrencies. However, I don't think people will believe that you could do it. So I don't think you can. That's my personal opinion. I don't know. I would love to be proven wrong. Yeah.
Great conversation. What are your thoughts, maybe are your inside knowledge about developments of offline capabilities with not stablecoin, but central bank digital currencies? And have you heard anything as well, too, collectively from different nation states in terms of how they're going to use maybe a basket of currencies or commodities or something else to actually back up the central bank digital currencies with the underlying asset?
Yeah, so I think two separate things. One is, how do you do an offline currency? There's generally two ways to do that. One is to have trusted execution and that kind of thing, and the other is more like eCash, Xiaomi and eCash, where the actual transfer just happens person to person, but you need to reveal at the end to collect your money. Essentially, you can't respend it. So respendable offline money, you're stuck with the hardware, and if the hardware gets hacked, we've seen some pretty big hardware hacks very recently. YubiKey and there's some other I think one of the Intel trusted execution environments recently got hacked as well. So there are problems with that. You can limit size of transactions and size of the amount that you're likely to hold to mitigate that, but it's imperfect. So offline is particularly difficult. You don't actually know you have the money until you go back and check online, generally. So that's a hard one. About backing it, I don't know. Do you need to? That's essentially, tokenization, stablecoins, they're all exactly the same thing. There's a big pile of something there, and then separately there's this token that we track. You kind of have to trust that the bond is maintained, and that's the weakest link in that chain. So.
I was thinking more so like, central banks are obviously accumulating gold and other kind of commodities, right? So as a stable coin, it's backed on fiat. So there could be different opinions and situations where one may be better than the other, or it could be geopolitical situations where one more attractive than the other. So what are your thoughts towards that?
Yeah. I'm the technologist, not the. I get to get out of jail free card because I'm the technologist. Yeah, I don't know. I mean, it really does depend on the reputation of the issuer. I'm not an economist. I'm just a technologist, so I don't really have very much for you. Yeah. We have one or two others, and then we gotta cut it, I think. So.
Yeah. Hey, can I do this one first?
Oh, there.
Yeah.
Sorry.
Hi.
Hey.
So one of the last parts of it, you basically were talking about a key inside of a smart contract, or basically the ability for a smart contract to sign transactions.
Yeah.
It's something we think about a lot, and wondering in that context, do you believe that would be the future on like a usability side, or is there any room for EOAs kind of coming in the next iteration of all this?
What's EOAs?
Externally owned accounts, like a normal.
Yeah. Right. So. I don't know. We'll see. Sort of which way it goes. Having some private information sort of requires that you have made a centralization trade-off that you might not be comfortable with. I guess it depends. One of the interesting things about the parsec system that we built is, you know, in a sense, you can think, well, we're sort of running all these shards, but we don't have to. We can take one and like have another entity run that. You know, like let's just say DTC runs it, and all the Apple shares are on that shard. So they could atomically update some, let's just say USDC transfer for one share of Apple, atomically. That's possible. I think that's likely how it'll play out. Less likely that you know, that something would hold a private key directly, and that would, you know, because you kind of have to trust whatever that service is for anything it's signed. Yeah.